Okay, I'm going to go ahead and start. I don't know if any more will be joining us. Okay, so we were partway through reviewing chapter 10. Okay, so get out something to write with and some paper. And where we left off was with the Grignard reagents. Okay, so I'm going to draw a structure and you tell me which, or you write down which starting materials you would use. Okay, so this is the alcohol. And what Grignard reagent and what carbonyl compound would you use to make this? I'll give you a moment to think about the answer. Okay, there's more than one correct answer for this. Okay, so the way to approach this, I'll go ahead and write this twice. Okay, we locate the CO bond, and then we break the next carbon-carbon bond. And then the part without the oxygen, which would be one carbon, that would be a methyl. Okay, that's our Grignard. And that could be bromide or chloride. Okay, the part with the oxygen, there's an H here that's not shown. Okay, since this is a secondary alcohol, we would prepare it using an aldehyde. Okay, so I removed this hydrogen and I made it a double bond. Okay, we could also disconnect it here. Okay, here's our CO bond. We disconnect it here. Okay, that means that our Grignard would be an isopropyl. And it would be this aldehyde. Okay, pentan 1-ol. How would you prepare this using a Grignard reagent? Okay, this time we have a primary alcohol. Okay, there's actually a couple of correct answers for this one. Okay, one way would be to use an aldehyde, specifically formaldehyde. We locate our CO bond, we break it here, and that would leave us with formaldehyde, just one carbon. Okay, we have two H's. And then we have a butyl group left, so this would be butyl magnesium bromide. All right, so that's one way. Okay, we could also use ethylene oxide. Okay, so that would give us a primary alcohol 2 carbons longer than what we started with. In this case, we would, instead of butyl magnesium bromide, we would use propyl magnesium bromide. Okay, followed by hydrolysis. Okay, I'm going to do one more. Okay, so 1,1-dicyclopentyl butan 1-ol. Okay, how would you make this? And there's 2 correct answers. Okay, this is a tertiary alcohol. Actually, I think there's 3 correct answers. Okay. One way would be to disconnect it here. Okay, we find the CO bond, we break the next carbon-carbon bond. Okay, so the part without the oxygen would be a propyl. Propyl magnesium bromide. And then this would be dicyclopentyl ketones. Right, we can also disconnect it here or here. Go this way. Okay, so that means we would have cyclopentyl magnesium bromide. And then we would have propyl cyclopentyl ketone. Okay, a third way would be to use an ester, since 2 of our alkyl groups are the same. And we would use 2 equivalents of cyclopentyl magnesium bromide. Okay, arbitrarily I chose the methyl ester, but it could be, this could be an ethyl group or any other group. Okay, so that's tertiary alcohol, so we could make, oh, sorry.
Is it possible for you to draw the mechanism for the last one?
Yeah.
The last one that you showed?
Yes.
Okay, thank you.
Okay. Okay, so that was, okay, so we got methyl butanoate, an ester. Okay. Carbonyl is polarized, carbon end is plus, nucleophile will attack the carbon nucleus. So this carbon is negative, this one is positive. Okay, so it starts out just like an aldehyde or ketone, just like that. Okay, so we formed a carbon-carbon bond. Okay, but at this point, this doesn't undergo protonation of the oxygen. Okay, something we'll learn next semester is that if you have an alcohol and an ether on the same carbon, that's usually unstable. Okay, and that would be the case here. Okay, so what happens next is that oxygen pushes down and it's going to expel OCH3. Okay, so this will give us propyl cyclohexyl ketone. Okay, and then OCH3 minus. And of course, this is a ketone, so a second equivalent. Can attack. Right, and then when we add dilute acid, when this is finished, then we get the alcohol. Okay, so last step is, make sure I'm not off screen. Okay, the next step is we'll add dilute acid, and that will give us the corresponding alcohol. Okay. Okay, besides an ester, okay, we could also use an acid chloride and two equivalents of the cyclopentyl magnesium bromide. Okay, we have to wait till this step is complete before we add the dilute acid. Okay, otherwise, Grignard is a very strong base, and this would simply react with the acid. And our product would be cyclopentane. Okay, there's several groups that will interfere with a Grignard reagent. Okay, for example, alcohols. Okay, if I try to attack the carbonyl with a Grignard reagent, it's going to pull off this proton. This is acidic enough. Okay, so other groups that are incompatible would be a terminal alkyne, SH groups. Okay, all of these are acidic enough where the Grignard would simply accept a proton before it attacked the carbonyl. NH groups as well. So if we had an amine, primary or secondary amine, the Grignard is strong enough to remove a proton from the nitrogen. Okay, Grignard is also compatible with incompatible, sorry, with groups like NO2 and nitrile group. Okay, we'll talk about Grignards and nitriles next semester, but if I had a nitrile, okay, and I wanted to just attack the carbonyl with the Grignard, I couldn't do it because the Grignard would also attack the nitrile. Okay, this is a Gilman reagent. Okay, so just show me the product, not the mechanism. Or I guess you won't show me, but I'm used to the interactive version of the class. Okay, so this is a Gilman reagent. And I'm going to react this with isobutyl chloride. Okay, so what's the product? Okay, this is in the chapter on alcohols. It's not really an alcohol forming reaction, but I think it's included because it's an organometallic like the Grignard is. Okay, so this is a coupling reaction that can be used to make alkanes. We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we would couple these two alkyl groups together. Even though there's a 2 here, we only use one of those isobutyl groups, so the byproduct here is isobutyl copper, and then we get lithium chloride as a byproduct. Okay, so only one of the alkyl groups is used. Okay, we can think of this as like a nucleophilic reaction. This carbon is negative, not as negative as a Grignard would be. And apparently, evidence suggests it's not strictly an SN2. Okay, but this isobutyl group replaces the chlorine. Okay, let's look at reduction next. Okay, some of the groups that we can reduce to form alcohols include esters, carboxylic acids, and aldehydes and ketones. Right, to reduce a ketone, okay, let's just choose acetone. Okay, there's a couple of different ways that we can reduce that to the corresponding alcohol. One is to use hydrogen and rainy nickel. We add a hydrogen here and a hydrogen there. Right, we could also use sodium borohydride, NaBH4. And we need a solvent that had a hydrogen bonding solvent. I'll just use water here. Okay, so sodium borohydride reductions can be performed in water. Okay, the difference between BH4 minus and water is that in water, hydrogen carries a partial positive charge. Oxygen is withdrawing electrons away from it. In the borohydride ion, hydrogen has a partial negative charge. Okay, so just like the Grignard, carbonyl is polarized, carbon edge is plus. H minus is a nucleophile, and it attacks the carbon nucleus. Okay, so we've added a hydrogen, and then in the next step, O minus picks up a proton from the solvent, and that gives us our secondary alcohol. Okay, so ketone will give us a secondary alcohol, and aldehyde will give us a primary alcohol. Okay, suppose we have both an both a ketone and an alkene present. Okay, we'll get different products depending on whether we use hydrogen rainy nickel or whether we use sodium borohydride. Okay, hydrogen and rainy nickel will reduce both of these groups. Okay, so we would get hexane 2-ol as our product. If we use sodium borohydride, this probably wouldn't dissolve very well in water, so let's use methanol. Okay, in this case, the ketone, whoops, here. Okay, the ketone would be reduced, but the alkene would remain intact. Okay, so notice the difference here. Right, lithium aluminum hydride is a stronger reducing agent. Okay, the mechanism works the same way as borohydride did. This is stronger. Not only will this reduce aldehydes and ketones, but it would also reduce esters and carboxylic acids and some other functional groups as well. All right, so if we have say this compound that has both an ester and a ketone, Okay, lithium aluminum hydride would reduce both of these groups. And okay, so we get this diol. We would also get methanol from the methyl ester. Okay, I have to have the 1 and the 2 here because lithium aluminum hydride is not compatible with water. It produces hydrogen gas in a very exothermic reaction. All right, with sodium borohydride, methanol, okay, sodium borohydride and methanol. Right, the ester would remain intact. Ketone would be reduced to a secondary alcohol. Okay, so sodium borohydride is not strong enough to reduce the ester. Okay, so here we have a ketone. Okay, and I sometimes see this. This is incorrect. That is, I sometimes see cases where you remove a proton from borane or BH4 minus. Okay, neither of those is correct. Okay, this has to come from the solvent, okay, water or methyl. Okay, BH3 and BH4 minus have electron-rich hydrogens. Okay, so they're actually going to repel the negative oxygen. Okay, let's look at thiols next. Okay, so draw 3,3-dimethyl. Pentane 1 thiol. 3,3-dimethyl pentane 1 thiol. Okay, pentane is 5. 3,3 dimethyl, and then a thiol is an SH. It's on carbon number 1. Okay, to review some of the properties of thiols, many of them have strong unpleasant odors. There are thiol compounds that are added to natural gas so that we can detect gas leaks. There are thiols that are present in skunk scent. Also, some foods with strong odors like onions and garlic. The odoriferous compounds contain either thiols or other sulfur compounds. Okay, next one, 3-mercaptophenol. 3-mercaptophenol. Okay, make sure you draw a benzene ring, not a cyclohexane. Okay, so this is phenol, and then mercapto is the SH. Okay, the phenol takes priority over the mercapto. Okay, in the previous problem, the thiol was the dominant functional group. In this case, it's not. Okay, so sulfur is not nearly as electronegative as oxygen. And so this affects its physical properties. Alcohols of similar molecular weight have much higher boiling points and melting points than the corresponding thiol. For example, methanol and ethanol are both high boiling liquids at room temperature. Ethanol boils at 78 Celsius. Methanol boils at about 69 Celsius. Whereas methane thiol and ethane thiol are both gases at room temperature. Okay, because of the lack of hydrogen bonding, thiols are typically quite a bit less soluble in water than alcohols. Okay, one notable chemical property of thiols is they're actually more acidic than the analogous alcohol. Okay, so if we compare say ethanol and ethane thiol, ethanol has a pKa of 16, 15.9, I think it is. Whereas ethane thiol has a pKa of about 10. So this is about 1,000,000 times more acidic. Thiophenol okay, this has a pKa of about 7. Okay, most carboxylic acids have pKs about 4 or 5, so this is not quite as acidic as the carboxylic acid. Okay, I haven't personally smelled it, but I've been told that thiophenol is one of the most horrible smelling substances there is. Okay, this means that if we have a thiol and we react it with, say, sodium hydroxide, okay, we can form the conjugate base. This goes to completion. Okay, this is about pKa 10. Water is 15.7. Okay, so this is product favored. All right, these thioate ions are good nucleophiles in SN2 reactions. Okay, so let's react this with 1-chloropropane. Okay, so write down the SN2 mechanism and the product that we would get from this. Okay. So this would come in, place the chloride. Okay, so we've got a propyl and a propyl, so this would be dipropyl sulfide. Right. We also looked at mild oxidation of thiols. So if I have, for example, two equivalents of a thiol, okay, I can do a mild oxidation. This would be, you could use something like dilute hydrogen peroxide or bromine and water. Okay, this forms a disulfide. Okay, so this would be called diethyl disulfide. Similarly, we could make a cyclic disulfide. Right, disulfides are stable compounds, unlike peroxides. Okay, peroxides are very unstable. They can explode, for example. Okay, this reaction I mentioned is reversible. We can reduce a disulfide back to two thiols. Right. The disulfide bond is, it turns out, is an important part of the structure of many proteins, and the fact that this reaction is reversible is also significant in biochemistry. Okay, I'm going to stop there. And on Wednesday, I plan to review Chapter 11 and Chapter 14, both of which are fairly short chapters. Chapter 11 was reactions of alcohol. So in this chapter, we talked mostly about how to make alcohols. In Chapter 11, it's starting with alcohols and converting them into other functional groups. And then Chapter 14 is ethers and epoxides.
What day is our final exam gonna be?
I was just looking at that. I have it written down. I believe it might be Wednesday. I'm not absolutely sure. I have that on my calendar. But I can send out a reminder.
Okay.
And currently I plan to post the final exam on Top Hat. Okay, and then the exam this Friday. Okay, that will be like the other two exams. I'll be sending out a Word document, and then you would scan your answers and send it back to me. Okay, I believe it's Wednesday, but I'll have to double check.